Alright guys, as I said in the last video, I told you yesterday that the whole next section was going to be all about this particle motion, this position, velocity, acceleration stuff. So it all goes back to multiple derivatives. You know, like position is the original function, velocity is the first derivative, acceleration is the second derivative because it's the derivative of velocity. And now keep in mind here that we use derivative, slope, rate of change, all kind of interchangeably here. You're used to, if you have physics or if you have taken physics, you know that velocity is the rate of change of position, which is why I say it's the derivative of position, and you know acceleration is the rate of change of velocity, which is why I say that it's the derivative of velocity, therefore making it the second derivative of position. So that's everything we're going to be talking about today. There's lots of keywords and definitions here. If you're in physics, this should be pretty much review for you. If you're not in physics, I suppose pay attention more carefully. So motion along a line, when we're talking about particle motion, as far as calculus goes, we can only go back and forth on either a straight horizontal or a straight vertical line. We can't do like diagonal motion or anything like that until later calc classes if you take them. So suppose an object along a coordinate line, so we know its position S, so we have here. Here's what we're going to write right here. So the position is equal to f of t. So the position is a function of time. The displacement is the change in position, kind of like your ending position compared to your beginning position. So this is from time t and then until time t plus delta t, so some sort of change in time. The displacement, we're going to write this as change of position, which is the position at the second time that we gave you, t plus delta t, and then minus the position at the first point, t. So in the average velocity, keep in mind, represents a slope. So we're going to write velocity and then a little AV down here for average. This equals displacement, which is the change in position, and then over the elapsed time. So that's just kind of a fancy way to write change in position over change in time. So we write delta S, which we just had up above, and then delta T is what we get when we take this quantity in parentheses minus this quantity, because the T's will cancel and we'll just be left with delta T. So that is just a sort of fancy version of the slope formula. All right, so to get an instantaneous velocity, we've already talked briefly about this. We have the average velocity on that formula up above. To get an instantaneous velocity, we take the limit as delta t shrinks down to 0. So the limit is the derivative, which is what I've kind of just been saying. So the instantaneous velocity, this is a velocity function that we talk about. This is v of t, and that is going to be equal to the derivative of the position function. And if we want to use our Leibniz notation, that is the derivative of position with respect to time. So a couple different notations there. So now many times they'll give us a formula for the position. Before, I think you guys even saw something like this on your limits test. You could only set up an average velocity, or we could estimate what the instantaneous velocity would be by kind of shrinking those intervals down towards 0. But now that we know our derivative rules, we can just straight up take the derivative of our position function. So velocity tells us direction of motion, which, like I said, if you're a physics person, that's easy for you. If not, velocity has direction. So if you're moving forward, velocity is positive. If you're moving backward, velocity is negative. Or if we consider ourselves to be moving right or left, if you're moving to the right, velocity is positive. If you're moving to the left, velocity is negative. So when the object is moving forward, the velocity is positive. And when the object is moving backward, velocity is negative. Or again, forward and backward, we can trade those out for right or left. So let's write forward or to the right, backward or to the left, because your particle will either be moving up or down or left and right. Okay, speed is very, very similar. Speed is what you think of like when you get in your car and look at the speedometer. You're never going to have negative speed. Speed is almost identical to velocity, except it takes on no sign. You can't have a negative speed, and so therefore we define it as the absolute value of velocity. Okay, so our first example. Now I mentioned with AP problems the quote-unquote funny-looking graph problem. I don't know if I've mentioned this before, but this is a great example of the funny-looking graph problem. So this is a velocity graph. So let's sort of make sure exactly what's going on here. The velocity graph, so we've got time. Anytime that you have time, it's going to be on the x-axis, and then this is a velocity graph. So as she's moving through, this is the velocity recorded by a motion detector. So it says describe her motion as a function of time. So it's a very, very vague statement. So we're just going to do the best that we can. So as we read through here, this, like from this point to this point, that's a positive velocity. And so if it's a positive velocity, that means she's moving forward. So first thing that we can write is that she moved forward. Again, because there's a positive velocity. For, this looks like, so if we look at this scale down here, the fact that the x values go from -4 to 36, that means that these are scaled by 4. So this would be 4, 8, 12, and then it looks like right there is where she crosses through. So let's say that's halfway between, let's say that's 14. So move forward for 14 seconds. And then if we want to get even more specific than that, what she's doing, because here the velocity kind of reaches a peak, so here the velocity is increasing, which means she's accelerating, and then holds constant, and then she decelerates back to a velocity of 0. So first she accelerates, held constant, and then decelerated. I feel like that has an extra C. Maybe? Question mark? Okay, so that's this pattern up until here. Then she stopped just for that instant, and then she turns around and she goes in the other direction. So here this negative velocity means that she's moving backward. So then she moved backward. Now this doesn't necessarily mean, and this is a stupid comment, but it doesn't necessarily mean that she's literally walking backwards, like she's not facing the way she's walking. It just means that she's moving in the opposite direction. So she moved backward from 14, this looks like 16, 20, 24, 28. So it looks like somewhere in here, this spot right here is actually where she stopped going backwards. So this looks like 16, 20, 24, 26. So maybe from 14 to 26 she was moving backward. So let's say for 12 seconds. So here, now this part's a little bit tricky. This part, since the velocity is decreasing, it seems like you should say that she's decelerating. But what's actually happening is the velocity is getting more and more negative, which means she's going backwards, but she's actually starting to move faster. Anytime you move away from the axis right here, you're going faster. You're either moving forward and getting faster or moving backward and getting faster. Because down here, the absolute value of velocity is speed, which is actually going to be a pretty large number. So this value right here, she actually is accelerating, even though she's going backwards, and it looks like the velocity is decreasing, which the velocity is decreasing. It's going from a small negative value down to a large negative value, which means she's going faster in the opposite direction. So she does accelerate first, and then she turns around right here and heads right back. Okay, and then it looks like she kind of just stands still for a second. So maybe from, we said this was 26, this is 28, 30, so maybe like for 26 to 30 or so. Oh, I guess that would be 32. So from 26 to 32. So she just stood still. There's no movement there. Okay, and then finally, she moved forward, and as she's moving forward, this velocity is increasing, so she is accelerating. So we're not quite sure what happened after this. We don't know if she stopped or what, but that's what it seems like is happening in the last little bit. So to answer the last question, when is her speed a maximum? Remember, absolute value of velocity is what we're looking for speed. So we're looking actually at this point right here. So her speed is a maximum even though she's going backwards. And this seems like it happens like 4, 8, 12, 16, 20, maybe like 21. T equals 21. So like I said, even though she's going backward, she still has the fastest speed. If you were to flip this part of the graph up above, like it was an absolute value curve, that point would be the highest on the absolute value graph. All right, second example. Particle moves on a line. Here's its position function. Anytime t is greater than 0, that's pretty typical. We're never going to talk about negative time. S is measured in meters and t is measured in seconds. So the displacement during the first 2 seconds. Remember the displacement we said is the change in position. So the change in position, we want to know what was the position at 2 and then minus what was the position at 0. So during the first 2 seconds. You can't just pick any 2 seconds. So the position at 2, we plug right into this function right here. So you'd get 4 minus 8 plus 3. So that would be a negative 1. So it looks like after 2 seconds they're 1 unit to the left or 1 unit down or whatever. And then minus the position at 0. We plug in 0 here. We get 3 for position. So my displacement is negative 4. And when we're talking about units, we would do meters, negative 4 meters, because position is all done in meters. So we would be 4 meters to the left of wherever we started, which makes sense. We started at 3, we landed at negative 1, so the displacement was negative 4 meters, which means it was 4 meters to the left of wherever the particle started. Okay, average velocity during the first 4 seconds. Average velocity, remember, is a slope. It's the change in, so V average is delta S over delta T. Change up a little slope. Keep in mind, average versus instantaneous. Two very, very, very different things. So change in position over change in time. Set up a little slope formula. So that would be the position at 4 seconds minus the position at 0 seconds, because during the first 4 seconds. And then over the change in time, which is 4 seconds minus 0 seconds. So same thing as before, we're just plugging this into the position function. So when I plug 4 in, I get 16 minus 16 plus 3. So I get 3. So after 4 seconds, their position was 3 meters to the right of center. And then minus, I know when I plug in 0, I get 3. So that means at the start, I was 3 meters to the right of center. And then over 4, what I end up getting is 0. So all that means, my average velocity, this means I ended up in the same place 4 seconds later. So I could have gone like back and forth. I could have done something in between. It's not like it just stays there, because we know at 2, it's actually somewhere else. So we get meters per second when we're talking about velocities. The average velocity was 0 meters per second. Then we want to find the instantaneous velocity when t equals 4. So instantaneous velocity, that's going to be an actual velocity function that we get by taking the derivative of the position function. Because now that we know derivatives, not that this formula is not useful, because sometimes we do want to actually know the average, and you'll want to know that on some different table problems on the AP test. But now that we know actual calculus and how to take derivatives, we can get the exact velocity at any point. So we take the derivative of our position function, which is right here. So the derivative of t squared, we do a power rule, the 2 comes out front, multiplies by the t, and then minus the derivative of 4t is just 4, because that piece is linear, and then plus the derivative of 3, which is a constant, of course, is just 0. So here's my velocity function, gives you the instantaneous velocity at any point. So we want it when t equals 4. So we want the velocity at 4. So we just plug 4 right into that function. And so we end up with 4, and that would again be in meters per second. Okay, our next question is about acceleration. So I'm going to see if I can just get this right on the same screen. So now acceleration, like we wrote on front, is the derivative of velocity. So the acceleration function, acceleration represents the rate of change of velocity, and so v prime would give us our acceleration function. So we've got the velocity function right in front of us. It's right here. If we take the derivative of that again, this is actually just a line. It's a linear function, and so the derivative is just the slope. The slope of this line is just 2. So the acceleration is 2. So now it says when t equals 4, well, the acceleration is constant. This tells us that the velocity is always increasing by 2 meters per second. So the acceleration is a constant 2 meters per second, or meters per second squared. So again, that means every second the velocity increases by 2 meters per second. That's the acceleration. So it happens to be constant here, so it's not like it really matters that t equals 4. And then is the speed increasing or decreasing at t equals 4? So this is something that's a little bit tricky. I'm going to make a note of this, and this is something that we'll talk about in class. Is the speed increasing or decreasing? So speed, remember, is the absolute value of velocity. And we talked a little bit about it when we were looking at this graph right here. We talked about how even though the velocity was going down, the function was actually speeding up. And that's because my velocity is negative and my acceleration is negative. So when my velocity is negative, that means I'm going backward. When my acceleration is negative, that means my velocity is decreasing. So if my velocity is negative and decreasing, it's going from like -2 to -4 to -6 or whatever. That means it's actually speeding up if you look at the absolute value. So that's the note that we're going to make here. So is the speed increasing or decreasing? This is a question that the AP test loves to ask. You have to take into account the acceleration and the velocity. So at t equals 4, the velocity at 4 was 4. The acceleration at 4 was 2. So here's what this means. The positive velocity means that my particle is moving forward. And the positive acceleration means my velocity is increasing. So the velocity is positive and increasing, which means it's going from, 4 to 6 to 8 to 10. That's definitely speeding up. So my speed is increasing at t equals 4. And the reason that I give, and I know I didn't ask for an explanation explicitly, but I'm going to explain it to you anyways, and that's because the velocity is positive and the acceleration is positive. So like I said, this is something we'll talk more about in class, but I'm going to make you guys a little note real quick. Note says if the signs, so positive or negative, of velocity and acceleration match, aka they're both positive or they're both negative, the speed is increasing. Remember, speed is the absolute value of velocity. So this one should be pretty self-explanatory. If they're both positive, yeah, the particle is increasing. And then the picture that I just showed you, this one right here, if my velocity is negative and the function is decreasing, so if my velocity is negative and decreasing, that means velocity is negative and acceleration is negative. This particle is actually speeding up. Notice that my velocity is getting farther away from the x-axis, which means its absolute value is growing. So that means the speed is actually getting larger. It's increasing because my velocities are negative and they're getting more negative, which means the absolute value is increasing. So now the next thing to write down is if the signs are opposite. So if you've got positive velocity and negative acceleration or vice versa, that means the speed is decreasing. Or in other words, that your particle is slowing down. So speed is increasing means your particle is speeding up. Speed is decreasing means your particle is slowing down. So let's again see why. So this region right here, for instance, my velocity is positive, but my acceleration is negative. And that's because velocity is decreasing. So if my velocity is positive but decreasing, that means my function is going forward, but it's actually slowing down because we're headed back towards the origin, which means we're headed back towards a speed of 0. So if my velocity is positive and my acceleration is negative, I'm slowing down. And then look at this part right here. This part right here, my velocity is negative but increasing, which means my acceleration is positive. So this little strip has a negative velocity below the x-axis, but a positive acceleration because the velocity is increasing. This particle is actually slowing down as well because my negative velocities are increasing, which takes them back towards 0. And so that would be slowing down, headed towards a speed of 0. All right, so we will talk more about that in class, and I know that's a little confusing. Physics people, you might be all over it, but it's going to be a little tricky, especially if we've never had physics before. Okay, so we want to describe the motion of the particle. So this mostly has to do with velocity. So let's just remind ourselves that the velocity is 2t minus 4. So we especially, let's even answer this question first, because that's going to help us describe the motion. So what values of t does the particle change direction? So the particle changes direction whenever the velocity switches signs. So when the velocity goes from positive to negative or from negative to positive. So the first clue to keep an eye out for is when the velocity is 0. So the velocity is 0 at, and we can just set this thing equal to 0, and really quickly we can see that we get a value of t equals 2. So the velocity is 0 when t equals 2. So one big part of these particle motion problems is setting up sign charts. So we've talked about sign charts before, so this sign chart is going to represent the velocity. It's going to tell us the sign, whether positive or negative, of the velocity. And we put 2 right in the middle because we know that that's when the velocity is 0. So if I plug in anything to the left, keep in mind though that I have this natural boundary of 0. They told me that my time is always going to be greater than or equal to 0. So say I plug in 1. If I plug 1 into this function, I end up with a negative velocity. Then if I plug in like 3, 4, 5 into this function right here, I end up with a positive velocity. So what that means is over here, right here, from 0 to 2, my particle is moving to the left, or it's moving backward, or whatever we want to say. So let's say moving to the left from 0 to 2. Now again, my acceleration is a constant 2 meters per second squared. So if my velocity is negative, but my acceleration is always positive, that means that my speed is decreasing. Okay, so it's moving to the left, but with positive acceleration. And so if it's moving to the left with positive acceleration, that means my values are negative, but they're increasing to they're headed towards 0. So this means that my particle is slowing down during that region, which should make sense. I mean, think about that. If it's going to come to a stop, it's probably going to slow down before it comes to a stop. And then from 2 onwards, then it moves to the right because it's got positive velocity. Moves to the right after t equals 2 with positive acceleration because my acceleration is a constant 2. And so if the velocity is positive and the acceleration is positive, that means my particle is speeding up. Okay, and just like last one, we are going to leave the AP problem for us to do together.